Assalamu alaikum wa rahmatullahi wa barakatuh. Good morning, gentlemen. Inshallah, today we are going to continue where we left off before week number 8. So, starting from today, we're going to start a new topic. So, up until now, we were talking about thyristors and their applications and their industrial applications in particular. Starting from now, inshallah, we're going to shift towards other applications, other devices. So, as you can see in front of you, we're going to be talking about regulated power supplies or power regulators. So let's start. So this particular circuit is familiar to us. We have seen it in the first experiment in the practical. So what is a regulated power supply? As you know, a power supply that you have been seeing previously in different labs is a device whose purpose is to supply an electrical power that you can control by controlling the voltage, right? So right here, for example, I have the electricity outlet. I have 120 volts, 60 hertz, and then I need to supply to my load here, my device. So this device could be for example, my laptop, right? So this will be connected to the wall. This point will be connected to the laptop. So the laptop, of course, is not going to take an AC voltage, and it's not going to take a high voltage that is 120 volts, that as in this case. So what do? The first step, we step down the voltage by this step down transformer, as you have seen in the lab. Then right here we have the full wave bridge rectifier, right? So right here, remember that right here the signal is going to look like this, right? So the full wave bridge rectifier is going to make everything positive, so pass the positive, and the negative part of the signal is going also to make it positive. After that, we have this capacitor, acts as a filter. So the job of this capacitor is to charge the signal, and then when it reaches the peak, when the signal goes down, the capacitor will discharge from its own charge voltage, such that the voltage is not going to drop suddenly, and the signal will look like that, right? And then it's going to charge again, then discharge, charge, discharge. So the resultant signal at this point will look like that. It will go up like this, then to be something like this, right? These are called ripples, right? And you have seen that these ripples, I can reduce it by either increasing the size, increasing the capacitance of the capacitor. But we said that this is not the most practical solution, because capacitors usually have large physical sizes, and as a result, it's not advisable to have too large values of capacitors, and instead we can have here a power regulator. So the power regulator here is going to fix the output voltage to the level that I need it to be, right? So the final output that is going to reach the load, hopefully, if everything goes fine, it should look like that. So which is something that's constant with time, which basically presents a DC signal. So this whole thing is a regulated AC to DC converter, right? So this is what you see inside the charger here, right? So it will step down the voltage from 120. This, for example, if the 10 ratio here is 10 to 1, so the voltage here is going to be 12 volt. And then after the other processes that take place here, the output voltage should be constant voltage like that, at 11 or 10 volt or whatever, depending on the settings or the parameters that you put here. So this is like the power charger. Here you have the power supply inside your PC. If you have a PC, this is the power supply. It does almost the same job. And this is the power supply that you have seen in the circuits and the electronic courses. So again, you supply the electrical output AC from behind here, and then you can set whatever, you can control whatever voltage that you want here. So you can set the voltage. You can also set the current limit, and you can give this constant DC voltage to your device. So this is basically what we mean by a power supply. Now the thing is that when you have this power supply, here we actually have what we discussed now. Here are the different steps of this circuit. We have talked about this before, right? And the practical in details. So this is the different steps. We have the transformer, full wave bridge rectifier, then the filter in the form of the capacitor. Here we have the full wave bridge rectifier. Here we have the transformer, and then we have the regulator. So hopefully and here you can see the output. This is the input, this is the output of the rectifier, this is the output after the capacitor, and this is the final output after the regulator. Now the thing is, when we have a power supply, let's say I have this power supply, and I'm going to set the voltage to any value that I need. Let's say 10 volt, okay? So I'm connecting 10 volt. So right here, I come to this power supply, and I set the voltage here to 10 volt. Now, when I connect the load, when I take the cables here and I connect it to my load, the load is going to have some particular resistance, right? Each load has its own resistance. So depending on the resistance, some current is going to come out, right? Now, when I have a power supply, one very important condition is that regardless of the resistance that I give to the power supply, if I put it at 14 volts, like here for example, if I set it to 14 volt, then I must get 14 volt out of it all the time. Okay, so when I have a power supply, I go to power supply. When I set the power supply to 14 volt, I expect that whatever load I connect here, I should get 14 volt, regardless, right? So if I come here, this is my power supply, regulated power supply, and here I have my load. Now, so this is the load here that I have here. Let's say this is the variable resistor. This is my load. So any value of the load here, if I put here 14 volt, then I need 14 volt actually to come out, to be supplied. But the thing is, this is actually not always going to be the case. Okay. Now, almost all the power supplies are going to have small difference. So if you put imagine that you put a very, very large output resistance, similar to an open circuit, like 10 giga ohm, and compare it to 10 ohm. This is a very high resistance. This is a very small resistance. Now, an ideal case, we should get 14 volt in both cases. سواء حطيت هنا 14 or 10 giga ohm or 10 ohm. But in reality, you're going to see, no, actually the voltage is going to be different. Here is going to be, the voltage here is going to be different than the voltage here. Actually, the voltage here is going to be high, the voltage here is going to be a little bit less. So this is going to be almost 14, this is going to be less than 14. Now, why is this happening? I mean, one of the main reasons that can happen is, first of all, the fluctuations that are coming from the wall, right? This power supply is connected to the to the wall, right? The 120, it's 120 volt. That's coming from the wall here. Now, if this input voltage can have some fluctuations. We call this the line. So you can see here, variation in the line voltage are expected. But a good power supply should be able to fight these or to resist these fluctuations in the line voltage. So even if the line voltage varies a little bit, fluctuates, and this especially occurs like in rural areas, like far villages and small towns. This can happen, especially in poor countries. This is quite typical to happen, very common to see. So the power supply, a good power supply, a regulated power supply should be able to give me this 14 volt, regardless of the fluctuations that happen here. If this goes up to 125, goes down to 115, still I should get 14 volt here. Okay, so this kind of regulation, it's called the line regulation. So the line regulation is the regulation or the way that the power supply is going to keep the output voltage, is going to keep this one 14 when this thing fluctuates, goes up and down. This is one of the sources of issues that you can have here, or one of the regulations that you require in the power supply here. The second thing is, remember that this power supply has its own internal resistance, right? And remember, always it depends on the load resistance that I have here. According to voltage divider rule, this 14 volt, actually some part of it will go here, some part of it will be lost inside the power supply. One way to eliminate this, as you remember from before week number 8, we said that one way to do it, I mean a very important feature about not power supplies but any devices that can output voltage, like amplifiers, voltage amplifiers for example, is to have a very low output resistance, right? So we need here to have a very low output resistance. Why do we need to have a very low output resistance? Because if I have a very low output resistance, according to voltage divider rule, all this 14 volt will go to my load. Nothing will be lost inside the internal resistance itself of the device. Okay, but still, if you have 10 ohm, this in itself is already very small. So you are going to reach a point, even if this one is, you can make it as small as possible, but because this resistance is actually very small itself, that's why you are going to get these fluctuations. That's why this internal resistance now is going to absorb some voltage. So here in this case, this output resistance is going to absorb some voltage, and when you put 10 giga ohm, it's going also to absorb a voltage, but it's going to be much less than the first case, because in this case, the output resistance is similar to this, but in that case, the output resistance is much less than your load resistance. That's why in this case, all the output voltage will go here. But in this case, when you put output resistance to 10 ohm, for example, or even less than that, like 5 ohm, 4 ohm, now the voltage is not going to be fixed. Why? Again, some part will be lost inside here. So if you have a good regulation, these fluctuations are going to be low. And these kind of fluctuations that happen because of the changes in the output resistance, the change in this 14 volt in this case is because the load itself is changing, not because the line is changing. It's because the load itself is changing. So when the load changes and I need this 14 volt to remain constant, this is called load regulation. Okay, so it's a regulated power supply will keep the 14 volt constant even if the load changes, even if this resistance, regardless if it goes up or goes down, it should remain the same. So these are the two kinds of regulations that we need to talk about, right? The load regulation and the line regulation. Load regulation is variation in the load value, the load resistance, and the line regulation is the variation in the line input voltage itself that's coming from the wall. Okay. So now we need to talk about how I can actually estimate or quantify this regulation. So we have the two kinds of regulation we need to talk about now. The first one is called the load regulation, right? So what is the load regulation again? The load regulation is when I change the load resistance. Okay, when I change the load resistance, I should have the voltage remain the same. Okay. Sometimes we can say the load resistance is changing, or we can say the load current is changing. It is the same thing, because when the load resistance, when the load resistance increases, the current will go down. If the load resistance decreases, the current will go up, right? So we can say that the load resistance changes or the load current changes. So how I can test? How can I say if this is a good load regulation or not? So these are the steps that I'm going to do. So this is my power supply. Assume this is my power supply here. How do I know the load regulation? How do I test what is the load regulation of this power supply? I will come here. 15 volt, whatever. Okay, Shabab. So let's say I'm sitting at a 15 volt. Now what I'm going to do, I'm going to do just as I did here, right? I'll put maximum resistance, I will put minimum resistance. If it's a good power supply, if it's a good well-regulated power supply, what should happen? If it's a good power supply, then the voltage in this case should be the same as this case, right? Because this is what I need. I need the output voltage to remain the same. So how do I put a very output resistance? A very large output resistance. A very large output resistance than the maximum output resistance that you can have. So not output, load resistance. How can I have here a very high load resistance? How do I put here? What do I put here? A very high output resistance is what we call an open circuit, right? So this case, just leave it like that. So now I don't have any load resistance. Just leave it open circuit. Okay? And in this case, what is the current that will move here? It is 0 ampere, right? It's open circuit, right? So I will look here and I will measure the voltage. I will see what is the voltage that I'm getting here. Okay, I should get I should get how much? 15 volt. So this value, we call it V VNL. Okay, what is VNL? Be careful, the notation here can be a little bit tricky. I have two voltages here. I have VNL, VFL. What is VNL? VNL is the load voltage, the voltage that I measure here, when I have no load current. What does no load current? NL معناها no load current. So what is the no load current? No load current معناها the current is zero. When do I get zero? When it is إيش? Open circuit. When I put open circuit here, right now. So right now I'll measure what? I'm going to measure the VNL, the no load voltage. So I'll take this value, I will record it. I will take it down, I will write it down. Then next what I'm going to do, now I'm going to, and instead of putting a very high output, a very low resistance like I'm doing now, I'm going to come and I will put a very small, the minimum resistance I can put here. طبعا what is the lowest resistance I can put? 0 ohm. But as you know, 0 ohm is actually a short circuit. And I cannot have a short circuit here. I cannot short this out. So every power supply in the data sheet, in the specifications, it will have its minimum resistance. The minimum resistance you can put here before this thing is destroyed. Why is going to be destroyed? Because the lower you make this resistance, the lower you bring it down, the higher the current will come here. So at one point the current will be too much and this will be destroyed. Okay, so each power supply will tell you what is the minimum resistance that you can have here. So it can be like 4 ohm, 5 ohm or whatever. So you look at that value, put it here, like 4 ohm, and then what do? What do you think? You measure the voltage again. But what do we call this voltage in this case? In this case the voltage is going to be called VFL. What is VFL? VFL is the load voltage with full load current. يعني maximum current this thing can give you. Maximum current. When do you get the maximum current? You get the maximum current when RL is equal to R minimum. And here you get this when RL is open circuit. You take these two values and then you apply them in this equation. Very straightforward. The load regulation is equal to VNL minus VFL, these two values, divided by VFL, multiplied by 100%. So you get a percentage. Now, again, what is the best case scenario? The best case scenario is if these two, what I need is a perfect power supply is going to, in this case, this voltage is going to be equal to that voltage. It's equal to going to be 15. This is what I want. I want to get 15 volt regardless of the load, right? So if this is 15, this is 15, put 15 minus 15 is 0. So 0, so what do you get? You get 0%. معناها the best case scenario if you get 0%. Now, if it's not a very good power supply, what's going to happen? These two values are not going to be the same, right? This case is going to be lower than that case. So this one is going to be lower than that one, right? And if it's lower, the bigger the difference, look here, the bigger the difference, the bigger the value that I'm going to get here. So actually the load regulation, it means that the lower the load regulation value, the better the regulator is. So I need this to be I want it to be as low as possible. I want it to be as low as possible. Okay? A perfect case when I get 0%. The bigger the load regulation, it means it's a poorly regulated power supply. There's a big difference in the voltage. It's not fixed. But this is the load regulation. Similarly, we have the line regulation. What is the line regulation? The line regulation apply this formula. It has a similar form, right? So here I have VHL, VLL, and VLL. What is VHL, VLL? VHL and VLL actually are the limits of the fluctuations that happen in the line. Okay, so this is the regulator that I have. This is my regulator. It's connected to the load, and here it's connected to the wall, the 120, like VRMS. Okay, so like this outlet, it can have some age variation. So you can see it can fluctuate between 105 to 125 fluctuations. Okay, it's just you cannot control them. This is coming from the power outlet that you are using for the power supply. So in this case, what do we call this? We call this VHL. You call this VLL. Okay, and you just apply it in this equation. Again, a good power supply, I need, if I put here 15 volt, I should get here as 15 volts all the time. Even if this goes up and down between these two values, I need this to remain 15, right? If this 15 changes, when the outlet changes, now this is not going to be equal to 0, and I'm going to have some value here. A perfect case, I get 15 minus 15. Oh, be careful. No, sorry, Asha. This is actually not VHL. This is a very common mistake. Be careful. This is not VHL. Be careful. Look, VHL and VLL are what? VHL and VLL are the voltage that I'm going to measure here. So when this is equal to 125, what do I get here? For example, I can get like 15. This 15 is VHL. So be very careful, Yasha. When this input source that I have here, it becomes 105, the measured voltage here is VLL. So it could be, for example, like 14. This 14 is my VLL. So I'm sorry for this issue. Yeah. So be careful. Don't make this mistake. This is a very common mistake. Okay. So these are not VHL, VLL. VHL and VLL are the values that I measure at the load. I want it to be 15. If I get here 15 volt, and here I get 15 volt, what is the answer here is going to be? It's going to be 0%. Again, perfect. Right? If I get, for example, 15 and 14, then it's not going to be 0, and I'm going to have some value that you can calculate. You can see here a well-regulated power supply can have a line regulation that is less than 0.1%. 1/1000, which is very, very good. When the voltage varies between 105 and 125. And here you can see the smaller the line regulation, the better. The smaller this value, the better the regulation is. Here we can also talk about the output resistance that we talked about. So the output resistance is what? It is the series or the internal resistance looking from the output side. Looking from the output. So this is the power supply. This resistance that I measure looking like that, this is my output resistance. And I need this to be, as we said, we want it to be as low as possible. Because the bigger the internal output resistance, the less the load regulation is going to become. Right? As we discussed earlier. Actually, they are related. They are related by this equation. So a good power supply has a low output resistance. Why? To minimize the voltage drop across it. To minimize the voltage that will be lost inside the power regulator itself. If a power supply has a low output resistance, its load regulation will be also low, which is required. Okay. So what is the output resistance? Output resistance here is calling it R Thevenin. So you can call it R Thevenin or you can call it R out. R out or R Thevenin is equal to what? You can use this equation. It's equal to VNL minus VFL divided by VFL. What is IFL? IFL is the maximum current. IFL is the maximum current. Is the maximum current that the power supply can deliver. When do I get this maximum current? It happens when R load, when the load resistance is equal to R minimum. لما تحط هنا, when you put this output resistance you set it at the lowest resistance possible, then you get this maximum load current. So you can use that equation. Or instead of writing it as VFL, you can instead use Ohm's law. So you can say IFL is equal to VFL divided by RL. Ohm's law, right? I equal to V over R. Then the denominator of the denominator can come up to the numerator here. So you can come out like that. So another way to talk about the load regulation, you can use this equation. to find the load regulation. Depends on the requirement of the question. You can use this equation if he has given you the voltages, and if he's given you the output resistance or Thevenin resistance, the output resistance of the device, you can use this you can use this equation. So the load regulation is equal to what? R Thevenin, which is here H R out, divided by the minimum resistance حقت اللود هذه, the minimum resistance multiplied by 100%. You can see that the smaller there is the output resistance, the better the regulation. Okay. Now let's see this example. A power supply has an output resistance of 1.35. Power supply, so what is this? This is R out, or R Thevenin, right? This is equal to 1.35. And the minimum load resistance of the device is R minimum is equal to 10 ohm. Then what is the load regulation? The load regulation is equal to, what did we say? It's equal to R out divided by R minimum. So in this case multiplied by 100%, of course. So in this case is equal to 1.35 divided by 10 multiplied by 100%, so you get 13.5%. So very straightforward. Very straightforward. Right. Now we need to talk about something also very important, which is called the load line. Okay, it's called the load line of this power supply. What's the load line of a device, Shabab? A load line of a device is actually a curve or relationship between the current and the voltage of the device at different scenarios. Okay. Right. So yeah, let me take this piece of paper. I'm going to let's have this thing here. Okay, Shabab, let's say I have a device with these parameters. I have a power supply here. I have a power supply here. Okay. When I put here open circuit like that, what do I measure? I measure V and L. So when RL is open circuit, what do I get? I get V and L. And in this case, let's say it's equal to, according to the question, is equal to 10.6 volt. Then when I put here the minimum resistance of this power supply, let's say the minimum resistance I put it, when I make RL is equal to R minimum, في المثال هذا في example هذا كانت 10 ohm for example. Okay, what do I get? I get the maximum current or full load. I get the full load that this device can give me. Here I don't have no load current, here I have full load current. And let's say when I put here R minimum, I get the voltage that I measure across it is 9.25. And let's say the current that we move in this case, current that's moving here, which we call it I, full load current, it's equal to 1 ampere. مثلا. So this is this case. What do I measure here? I measure here VFL. This is the case when I put R minimum. The second case, when the power supply, the same power supply, I don't put anything here. I keep it open circuit like that. What is the voltage that I measure here? This is the VNL. What is this current? This is INL, which is obviously 0 ampere, open circuit. Okay? And he will ask us draw or plot the load line of the power supply. Also, we can also find the load regulation. So I'm finding the load regulation and I'm going to plot the load line. So how do I plot the load line? That's very simple steps. So the load line is going to be a curve between the current of the device and the voltage. Okay, شباب. Now which voltage that I'm talking about here? I'm talking about the output voltage here. So this is the output voltage. And this is the current that will move to the load. So this is the load current. This current moving into the load. Now right here I have two extremes. I have the two extremes of the device. I have it when I have no load current, when I have the maximum load current. What is the no load current here? It is 0 ampere. So it is right here, this point. Right? This current is here is 0 ampere. What is the maximum current? The maximum current in this case, according to what you have here, the given information here, it is 1 ampere. So the maximum here is actually 1 ampere, like that. Now what do I need to do? I need to see what is the voltage, what is the output voltage in each of these two cases. When the load is here, when the load current is like this, when do I get this, by the way? I get this when RL is open circuit. When do I get this? I get this when RL is equal to R load minimum. I get the maximum current, right? When the load resistance goes down, the load current will go up, obviously, right? So I need to see what is the output voltage in these two cases. A perfect scenario, a perfect device, what's going to happen? The voltage should be the same. I should get a straight line like that. You agree? I should have a straight line like this. This is because this is how a power supply, a well-regulated power supply should be. Regardless of the load, I should get the same voltage. I should provide the same voltage. But right now, because of imperfections in the device, this is not going to be the case. Here I'm going to get some voltage. Here I'm going to get a little bit smaller voltage. Okay, so obviously these values that I have here, right? So when I have no load current, which is this value, what is the voltage? It's 10.6. So we'll go here, I'll come here, I'll put 10.6 volt. What is the second value that I have? What is the value that I have in this case? It is, so right now, this is the point. When I have 0 ampere, I get this voltage. When I have 1 ampere at FL, what do I get? I get 9.25. So right here, I have 9.25 volt. This is this point. So you can see these 2 points are actually the two extremes. The two extremes of the load line. And all you have to do is what? Just connect straight line between these 2 points. Okay? Now a perfect case, it should be a straight line, right? I should get the same voltage. But right now you can see the voltage is not the same. This is the difference. So this difference is what we call the load regulation. The smaller this difference is, the better the load regulation becomes. So what does this difference represent? It can also be related to what we call the slope, right? What is the slope of this line? Can I get the slope of this line? The slope of this curve is equal to what? Delta y over delta x. Do you agree? What is delta y here? It is v delta v over delta I. Right? What do you call the v over I? The resistance, right? So this actually gives me the resistance. Which resistance? The output resistance. But be careful, the slope here is negative, right? It's going down. The curve is going down, right? So it's actually 9.25 minus 10.6 divided by 1 minus 0. So in this case, it's equal to it's equal to 9.25 minus 10.6. This is delta V. How about delta Y? Delta Y it's 1 minus 0, which is the current, right? And what does this give me? It will be a negative value, right? How much is that? Here I have 0.75 plus 6, so you get 1 minus 3.5. Okay, this is the value that was given us in the previous example. no, sorry, this is minus 1.35. So this is not, this is the value, and this is equal to h, is equal to minus r out. This is minus r out. And it means that r out will device equal to h 1.35. Which is quite small, right? And the smaller this value, the better the regulation is going to become. Right? Because the smaller this value, the smaller this difference is going to become. So this line will be more of a straight line. Okay? If I want to find the load regulation, quickly, the load regulation is equal to h. I have two ways. I can either say it is v, I can use these values. So I can say it's equal to 10.6 minus 9.25 multiplied by 100, multiplied by a 100%, oh sorry, divided by 9.25 multiplied by 100%, and this is equal to what? Or I can say it's equal to, or I can say it is equal to r out divided by as we did, divided by r minimum, right? We did that in the previous part of the, what is it? Yeah, did that here, right? So you can use this one here. So if I do that, what's the answer that I'm going to get? I get 13.5%. Okay, so this is how we can tackle these kind of questions, right? Yeah, 13.5% like this. So I hope this clear. It's very straightforward. It's just important to, the application of the equation is easy, but we need to understand what is happening here and how we can actually do the test ourselves. How we can test the load regulation of the device ourselves. Okay. Now in practice, we have two kind of regulators that can be implemented. We have shunt regulators and we have series regulators. Okay, so the power regulators, they can actually be designed in two different ways, two different types, shunt and series. Shunt means what? Shunt means parallel. Okay, the word shunt means parallel. So we have parallel or shunt. So a different way of saying parallel. Shunt power regulators and series power regulators. So right now we'll start with parallel power regulators, and inshallah next lecture we'll talk about series power regulators. I'm going to see what are the differences and what are the applications of each type. So we're going to see that the designs that I'm going to have, they're going to all be like, we are going to have different ideas, but in all of them, we're going to have in the core, in the heart of all these regulators, are going to have a Zener diode. Why a particular Zener diode? Because this is the property, or this is the job of Zener diode, is to maintain the voltage across it, and anything parallel with it constant, right? As long as it's operated in the Zener mode, okay? As long as it's operated in the Zener mode. So the simplest form of a regulator or a shunt regulator is the Zener diode circuit that we have here. So here I have my input power, the input voltage coming from here. This is the load. Okay, what is this? This is RS. So for any, we'll talk about this series resistance, but let's talk about this output voltage first. Now, is this output voltage going to be constant? Yes. How do I know that? Because I have the Zener diode here. It's connected in parallel, right? So as long as this V input is greater than, VZ, then the Zener diode will be acting in the Zener mode. If it's acting in the Zener mode, it means the voltage here will be equal to VZ. And I can say that V out, which is parallel with the Zener diode, will have the output voltage will actually be equal to VZ, because it's parallel with it. So the Zener diode operates in the Zener breakdown region, and it produces a constant voltage, or the regulation voltage equal to VZ across it, VZ like that, and anything parallel with it for sure. Now, how is the regulation action taking place? You can see here, when the load current IL changes, the Zener current will counteract this change to keep the current coming here constant. Okay, we'll see that also. We'll see all of this, what it means. But for the time being, we need to talk about, we need to analyze the circuit here itself. Now, again, what is the output voltage? The output voltage in this particular circuit is simple. It's just VZ because it's connected parallel with it. How about this load current? How about IL? This current, IL. How much is this IL? You just apply Ohm's law. If the voltage here is equal to VZ, معناها IL is equal to what? It's equal to V out divided by RL. But V out is VZ, right? Just sit here. معناها IL is equal to VZ divided by RL. Very simple. So the current here is equal to VZ over RL. طب how about this current هذا, this current is called IS, current coming from the source. This current, how much is IS? Now in order to find the current IS, what I can do is I can apply Ohm's law in this resistance. So I can say that IS is equal to, how do I apply the current here? It's equal to Vn, the voltage before, minus the current, the voltage after, divided by the resistance. So it's equal to Vn minus, what is the voltage here? The voltage here is VZ, is V out, right? So Vn minus V out, here VZ, can act as VZ or V out, divided by RS. What can we notice? Now Vn, it's constant. RS obviously is constant. Is V out constant? Yes, it is constant because of the VZ, because of the Zener. Now what can we say about this IS? IS will always also be constant. And this is actually a property. This is a feature of shunt regulators. So you can see here with any shunt regulator, a change in the load current is complemented or balanced or countered by an opposing change in the shunt current. This current basically. يعني ايش؟ يعني if IL tries to increase by 1 milliampere, if this current tries to increase, go up, how can this current go up? If the RL goes down. So if you decrease RL, this current will try to go up. What is the Zener diode going to do to counter this? Because again, if this current increases, معناها this current will try to increase also, right? Because this current is coming from here. But what is the Zener diode going to do? If this thing tries to increase by 1 milliampere, the Zener diode will decrease by 1 milliampere. This current اللي هو ايش نسميه IZ. IZ is equal to what? IZ is equal to what in this case? It is equal to this current IS minus IL. KCL, right? By applying KCL here. So if IL tries to go up, to go up, IS will go down. IZ will go down. Okay, so to balance, if this goes up, this will go down. طب لو العكس, if this tries to go down, this will go up. At the end, المحصلة إن هذا دائما يصير ثابت. Okay, so this is a feature. This is a feature of shunt regulators. How can I say if this is a shunt regulator? I will look at IS. If IS is constant, it does not change, regardless of whatever I do here, خلاص, I know this is shunt power regulator. So this can come like a trick, right? I can ask you, calculate or tell me how much is IS. بعدين أقول لك غير R خليها كذا, change it, then give me what is the new value of IS. So since the regulator shunt power regulator, you don't do anything. You say it is still the same because it's a shunt power regulator. How then does the Zener diode keep the voltage here constant? And we have seen that it will counteract or counterbalance the change that will happen here. So the Zener diode keeps the voltage across it constant by keeping this product. So you can think of the Zener diode as a resistance. انت تتخيل ان Zener diode, this Zener diode, you can imagine that the Zener diode is acting as a resistance. But this resistance is a special resistance. هذه بنسميها RZ. وهنا الفولتج هنا, this voltage is called VZ. and this current, let's call it IZ. So how does the Zener diode keep this VZ constant? Because this is the property of a Zener diode, right? It keeps the VZ, the voltage across it, constant. How does it keep it constant? This is what it does. Remember, what did we say? This IZ is going to change. This load, right? This load, when it tries to increase, the current tries to increase, the VZ will counter that by decreasing its own current. والعكس صحيح. At the same time, the Zener diode keeps this VZ constant by doing the following. What is the voltage here? What is this VZ equal to? VZ is equal to IZ multiplied by RZ. Just Ohm's law, right? Multiply this resistance by this current, you get VZ. Okay, this is fine. Now what happens? What do you think? What happens if IZ goes? What happens if IZ increases? When IZ increases, the Zener diode will decrease its own RZ. So again, look, VZ equals to RZ multiplied by IZ. When the current in the Zener increases, what will happen? The Zener diode is going to decrease its own RZ. So if this increases by 50%, what will happen to RZ? Will decrease by 50%. فالمحصلة بتبقى زي ما هي. If this increases twice, this will go down twice. If this is doubled, this will be half. والعكس, if this becomes half, يعني لو current هنا صار يقل, what it's going to do? If this, like that. If this goes up, this will go down. But what if it's the opposite? لو IZ, if it tries to go down, RZ will go up. ايش اللي بيصير؟ المحصلة بتبقى زي ما هي. يعني مثلا ممكن تقول RZ for example is 100 والcurrent is 2 ملي. كم المحصلة؟ 2 milli multiplied by 100, how much? Let's say it's 1000. So you get 2 volt. طب let's say current حق IZ now becomes 4 milliampere. ايش بيصير في RZ? It will go down. It will be actually 500. فالمحصلة كم بتصير؟ It will still remain 2 volt. هذه 2 volt هي VZ. طب how is RZ changing? RZ actually, this RZ that we're talking about, this is actually the resistance of the depletion region. Remember the depletion region? Here I have the PN junction of the diode. This is like RZ. So the Zener diode in the Zener mode, when the current passes like that, when the current passes like that, because it's reverse biased, in the Zener mode, when the current passes like that, this resistance actually is going to react to the amount of current. The higher the current that is passing, the smaller the depletion region is going to become. والعكس, when the current becomes less, the depletion region becomes bigger. The depletion region becomes bigger معناها bigger RZ, bigger resistance. So this dynamic relationship between the IZ and RZ, what keeps VZ constant. Increase this decreases. Decrease this increases. محصلة هذا ثابت. So this is how you think of a Zener diode. Like a Zener diode, you can think of it as a resistance whose resistance تعتمد على قيمة قيمة الكرنت. The higher the current, the smaller the resistance. كل ما هذا زاد كل ما هذا نزل. Such that this will remain constant. طيب متى when does IZ go up or go down? IZ is here. This is IZ. When does IZ go up and down? It goes up and down depending on the value of IL. And IL تعتمد على قيمة RL. So when you change the value of RL, the voltage هذا بيحاول يتغير. For example, you try to decrease this resistance. فالvoltage هذا is going to try to change. Alright, now before the Zener kicks in, if you make this resistance smaller, so pay attention with me, Aisha. If this RL tries to go down, IL will increase. When IL increase, what will happen to the IZ? It will decrease. Remember, IZ عكس IL, counterbalance. If IL increases, this IZ will decrease. When IZ decreases, what will happen? Remember here, الكرنت هذا ما ينزل، ايش بيصير في الريزيستنس؟ it will go up. اوكي؟ فالمحصلة ايش؟ صح ان الفولتج هذا يحاول ينزل، لكن ايش الزينر دايود لما الكرنت اللي ماشي فيه when it tries to go down, the resistance here will increase and you get again, so instead of the voltage going down, it will just remain the same because the zener diode is keeping this product هذا constant. Okay شباب, so this is basically how the device or how the zener diode can regulate the voltage. So here I actually have the steps. Here you can how we find IS. So remember, here we have some points. The maximum current with regulation occurs متى؟ لما يكون yes, the maximum load current when regulation happens when I is equal to 0. ففي الحالة هذه all the currents coming here will come down like that. In this case IL is equal to IS. Alright. Now the most important part here is that this current IS is always constant. It's fixed. Okay, it does not change. It's here because this is constant, this is constant, this is constant. A change in the load current has almost no effect on the input current. هذا IS input current IS. This is a very important feature. هذه feature اللي ايش تكلمنا عنها. This is a very important feature. Now this is fine, but actually we have an issue here, or actually have two issues. The first issue is we have two issues with this design. What are the issues of this design? The first issue is remember that the zener diode is temperature dependent. The zener diode is typically temperature dependent. Right? What does it mean? It means that when the device heats up, which is expected and typical in the case of power regulators, when the device heats up, what happens? This value of Vz changes a little bit. ليش؟ لأن RZ نفسها تتغير. Remember, resistance في العادة, and usually it changes a little bit with temperature, right? So yes, the zener diode, or actually any diode, the characteristics are sensitive to temperature. And this sensitivity to temperature becomes even worse, becomes more and more, the bigger the Vz becomes. Then RZ will become more. Okay? So remember from our discussion previously, we said that we have said that the minimum temperature dependent point is what? When I make Vz, the temperature Vz equal to between 5.6 to 6. These are the temperature independent. Temperature independent. Okay, but the issue is here, suppose I want this output voltage to be 10. I don't want it to be 5.6. So the only way to do that with this design is to use 10 volt here. So this issue will come. So if I want this 10 volt to happen, after some times I will see that Vz actually is not 10 anymore. It has changed. Why did it change? Because of temperature. This is the first issue, the temperature dependence. The second issue is that sometimes the current that will pass here, actually the current IZ can be too high for the zener diode. So I have two issues. This current can be too high for the zener diode. Second issue, and this current is important because this current is the key to how we balance the output voltage here. The second issue that I have is this temperature dependence issue that we have. Okay, so now we are going to see designs that how we can tackle each of these issues. The first issue is to solve the issue of the current. Okay, so what is the difference in this case? The difference is, instead of connecting the zener diode into the ground right away, like this, instead of having my zener diode connected to the ground directly like that, here instead, It is connected to the base of a transistor and then go down. Now what is this? What is the job of this transistor and why am I connecting it to the base in particular? I'm actually doing that in order to limit this IZ, to make it small. Okay, I want to make this IZ as small as possible. Right? So in this case, what do I have? What are the differences in the design? Let's first talk about V out. So to get V out, what is V out equal to? Now, هل V out, is it parallel with the VZ? No, it's not parallel with VZ alone. How about V out? V out is equal to what according to KVL? It's actually equal to VZ. From here to here is VZ. Plus from here to here. Till ground. What is the voltage from here to here? Look, from here to here. What do we call this? This is called VBE. How much is VBE? Of a bipolar junction transistor? It is 0.7. So now we have a small modification. V out, it's not equal to VZ alone. We actually have to add VB. So it's equal to VZ plus VB. Okay, this is for this is for V out. How about IL? IL is still the same. It is equal to V out divided by RL. Straightforward. My apology. How about IS? IS also the same. It is equal to Vn, the voltage here, minus the voltage here, divided by RS. Constant, constant. And remember, this VB is constant, right? And VZ is also constant, and this is always 0.7. VZ is constant. That's why still V out is constant. Regulated, right? This is what we want. Right? That means that this IS, current هذا, IS is also constant. IS is also constant, right? This current. But right now we have a new current. We have actually two currents. We have this current. We have only one current. اللي هو ايش؟ ممكن نسميه IC, the collector current inside here. Before I talk about IC, let's talk about IZ. IZ in this case equal to what? If you look carefully, you can see that IZ is actually the same as IB of this transistor. What do we say about IB? We say IB is almost إيش؟ Yeah, IZ هي نفسها is equal to إيش؟ IB, which is almost equal to 0 ampere. Right? So it's almost equal to 0 ampere. So this current is almost 0. And this is what we want. We don't want this current to be high. So now the Zener diode can now take this current. It's not too high to it. And when this current is small, this thing is not going to heat up as much. And when the IZ is high, this passage of current is going to increase the temperature of the Zener diode. But right now, since the IZ is smaller, then the Zener diode is not going to heat up as much. Okay. So you have solved almost, and we're actually solving both issues, not entirely, but helping them a lot by a large degree. Okay, sure. Now, if I talk about this current collector, the collector current, IC, what can I say? How much is it equal to? I will apply KCL in this node. What does KCL say? KCL says that IS, the current entering into this node, the IS, is equal to إيش? It's equal to IZ. Right, this current is equal to IZ plus IC plus, what do you call this current? We call it IL, load current. So it's equal to IZ plus IC plus IL. What did we say about IZ? We said that it is almost equal to إيش؟ 0. لأنها إيش؟ base current. So we can say that IC almost equal to إيش؟ If I do rearrangement, take this to the side, so it is almost equal to IS minus IL, almost. If you want to find what is the accurate expression, the accurate expression is IC is exactly equal to IS minus IZ minus IL. Like, and again, IZ is almost 0. That's why it can be approximated like this. Okay, and here ahead, just explanation of what we discussed right now, nothing new here. Have an example. We can solve this example on the discussion that we had right now. So in this figure, Vn is equal to 15 volt, Rs is equal to 10 ohm, Vz is equal to 9.1 volt. See, it's not temperature independent. But still, since this current is going to be too low, so it's not as bad as the previous issue. But still, I have the temperature dependence issue. Still, I'm suffering. Still, I'm suffering from temperature dependence. Why? Because this is high Vz. It's not in the range that you want, 5.6 up to 6 volt. VBE, this voltage, is equal to 0.8 volt. And RL is 40 ohm. This is 40 ohm. What's required here in this question? Find what are the values of output voltage. So what's V out? Input current, IS. Load current, IL. And collector current, IC. Okay, so this is a very straightforward example. Let's start with V out. V out in this question is equal to what? In this circuit, V out is Vz from here to here plus VBE. Vz plus VBE. Plus VBE. How much is Vz in this question? Is given to us 9.1. How much is VBE? It's 0.8. Means V out will be 9.9 volt. It will be fixed at 9.9 volt. Right. What is the input current? And what is the load current? Since we got to the output voltage, let's get I load right away. So I load is equal to V out divided by RL. So it is equal to 9.9 volt divided by, how much is RL? RL is 40 ohm. Divide this by this, how much do we get? You get 248 milliampere. 248 milliampere. How about IS? Remember, IS is constant. The constant equal to what? It's equal to Vn minus V out divided by Rs. Constant. Sorry, RL. Oh yeah, Rs. Yeah, Rs. Constant. How much is Vn? The question, 15. How much is V out? We just found it here, 9.9. How much is Rs? 10. Do that, you get 510 milliamps. 510 milliamps. Let's do here IC. What is the approximated value of IC? Approximately IC is equal to IS minus IL. So 510 minus 248, we get 262 milliampere. Okay, 262 milliampere. Now he's giving you here a practice problem. Try to repeat this problem by changing Vn to 12 volt and Vz to 6.8 and see how are the new values. Same requirements are going to be. Right. Now we move to a new design. We have seen the issue of the low current. You can see now the Zener diode. I'm not going to have high current moving in anymore. It's almost zero. Because it's connected to a base of a bipolar junction transistor. Now in this design, we solve the other issue, which is the temperature dependence issue. We said that the temperature independent value, temperature independent value of Vz is what? 5.6 volt. So how can I use 5.6 volt here and at the same time get whatever voltage that I need here? Because remember in this design, يعني VBE is always 0.8. In this case, VBE is always 0.8. I don't have much of a freedom to choose VZ that I need. That's why I need to choose 9.1 volt here. If I want this voltage to be 9.9 volt, معنى الحل الوحيد إني إيش choose 9.1. This is the only solution that I have. But with this design, actually, we can use 5.6 and still get whatever voltage that we need here. Now, how are we going to do that? Let's see. So you can see now we are adding different things in our design. طيب. Remember, شباب, we need to come up first with the equation for the output voltage. هل فعلا output voltage is it fixed or not? voltage. So V output here, if you look carefully, V output here, according to KVL, what is it equal to? You can see that V out is equal to this voltage. See, this is the voltage that I have here, right? It's equal to this voltage plus this voltage. Do you agree? It's equal to this voltage plus this voltage. This is correct. So I can see it's equal to VR2 plus VR1. Okay, but the issue is this voltage that I have here, this is V out. I can do that. But if you look carefully, look at R1 and R2, they are actually connected in series. But somebody can say, actually they're not. I have some current will move here, so they are not series. But what do we say about this current? This current is almost zero, right? Because base, again, it's a base of a transistor. It means that yes, R1 and R2 are actually approximately they are series. If they are series, what can we say? We can say that I can apply voltage divider rule here, right? So the voltage from here to here is V out. But the voltage from here to here, what do we call it? See, from here to here, what do we call the voltage from here, this point to this point? I can call it VR1. Sorry, VR1. Okay, from here to here I have V out, from here to here I have VR1. Is there a relationship between V out and VR1? Yes, I can actually say that VR1, let me write it here. What I can say that VR1, I can say that VR1 is equal to H, apply voltage divider rule. So it is equal to, this voltage is equal to this resistance, هذه, divided by the total resistance, which is R1 plus R2, multiplied by the total resistance divided between them. What is the total resistance I'm dividing between them? V out. Multiplied by V out. See? I have a relationship between VR1, the voltage, this voltage, and this voltage up here. طيب, what can we say about VR1? VR1 actually in this design is constant. The VR1 is actually constant. How is VR1 constant? Look from the left side. See, VR1, if I apply KVL in this loop, what can I say? I can say that this voltage from here to here, which is VR1, it is equal to H, it's equal to this voltage, which is VBE, right? From here to here is what? It's VBE. So I can say that VR1 نفسها from the left side is equal to what? It is equal to VBE from here to here. Plus, what is the voltage from here to here? It is VZ, right? This is VZ. So plus VZ. From the left, this voltage from the left is equal to VBE plus VZ. From the right or up here, what is equal to? I can apply voltage divider rule or reverse voltage divider rule. So I can say, voltage divider rule. So I can say that VR1 is equal to R1 divided by R1 plus R2 multiplied by this total voltage, which is V out. So can you see here what I'm going to do? I need to see what is V out. So this is my goal. And this is equal to this. This is equal to VR1, or VR is equal to this. Means this is equal to this. These two things are equal. Right? So what I'm going to do? I'm going to say that VBE plus VZ is equal to R1 plus R2 divided by V out. And now since I want to know what is the equation, what is the formula for V out, I'll just do a cross product to rearrange. So what do I get? I get multiply the cross product like that. So what do we get? We get V out equals to R1 plus R2 divided by R1 multiplied by this whole thing, VBE plus VZ. Now, is V out now constant? Yes. Why is that? Because I have R1, yeah, R2 here. I have R1 constant, R2 is constant, R1 is constant. How about VBE? Constant, 0.7. How about VZ? Constant, VZ. It's a Zener dial. Okay, so now we can say that yes, indeed, V out will be regulated, will be fixed at a certain value. Now, what is the good thing about this device? The good thing is, I can always keep this thing fixed at 5.6. I can put whatever, I can keep this 5.6. So how can I make this 10 volt? If this 10 volt or 20 volt or 30 volt, any output voltage that you need, you don't need to change VZ. Keep it 5.6. VBE still 0.7. Don't change it. Keep. And this you cannot change this, of course. But 5.6, keep it. Why do I want it to be 5.6 again? Because this is the temperature independent value. So how can I make this thing equal to 20 volt or 30 volt or to give it any value that I need? By playing with H, by playing with this ratio. By playing with this ratio. So actually here I can have R2, I can have R1 as a variable resistor, or R2 as a variable resistor, or both of them as a variable resistors with potentiometers. And then I can play with them, I can put the correct values that will give me V out that I need, while keeping VZ equal to 5.6. Okay, so now I'm choosing the temperature independent VZ value, and at the same time I'm getting the whatever output voltage that I need. Okay, and this is why this design is very good in this aspect. This configuration is called a reverse voltage divider. So I'm using reverse voltage divider. Look here, reverse voltage divider to get the value that I need. So what is V out? V out is equal to R1 plus R2 divided by R1 multiplied by VZ plus VB. And be careful, sharp. The values, just don't memorize the equation. You need to understand it, because in the exam he might call this R1, call this R2. So you need to know that R1 is this resistance. This is R1, the one that is lower, below here, because this one is the one that is connected to the Zen, or shares the same voltage as VBE plus VZ, according to KVL here. Yeah, we didn't talk about the, I need to talk about IL. IL is still the same, just V out, whatever V out you get divided by RL. How about IS? Still the same, right? IS is equal to Vn minus VES divided by RS. How about IC? This current. This case, what is this equal to? In this case, Shabab, look, I have IS. Here I have IL. But still, here I can have a current also, right? Here I have current moving inside here. What do you call it? You can call it IR. So what is the relationship actually? What is the relationship here? The relationship is that IS, apply KCL. This current that's entering here, IS, is equal to ايش؟ is equal to IC هذا plus IR, that current moving in the resistors branch here, plus I load IL. This is correct. معناها ايش؟ معناها ان IC is equal to ايش؟ is equal to IS. Rearrange the terms. IS minus IR minus IL. But the thing is, you're going to see that in order to make the device, in order to increase the performance, to make it the device has a higher, to make it the device have better efficiency, as we're going to see, it is always better to increase. يعني this, let's say that you designed your system, designed your circuit, and you have seen that you need R1 to become 100 ohm, sorry, R2 100 ohm, R1 200 ohm مثلا, for example. So instead of putting 100 ohm and 200 ohm, what you can do is keep them 100 and 200, but make them kilo ohm. So instead of putting 100, 200, make it 100 kilo, 200 kilo. So this is called keeping the ratio the same. Increasing the values of R1, R2, increase the values of R1, R2 while keeping the ratio the same. النسبة حقتهم خليهم يعني this keep ratio the same. Keep this the same, but R1 or R2, instead of make them 100 and 200, make them 100 kilo, 200 kilo. What do I gain by doing that? If I make this resistance high like this, what happens to this current? It becomes, if R1 and R2 are high, then what do we get? What happens? Then IR becomes ايش? very small. Becomes very small, almost zero. So I can say this is, most cases in a good regulator is going to be equal to 0. It means this IC approximately, if this is equal to 0, I can approximate it as IS minus IL. Okay? So it is almost the same as it is the same value, the same expression that we used for the older design, without having R1 and R2. Still the same it is still the same, form that we have here. IS is equal to IC is equal to IS minus IR. Approximately, of course. Okay, شباب. Let me just adjust the focus. Yeah. Yeah, so these are here you can see the explanation that we discussed right now. This is the value of IC. So IC is almost equal to IS minus IL. This equation is approximation. It does not include the current through R1 R2 اللي هو ايش؟ اللي هو IR. But again, IR is usually ايش؟ very small to neglect. This is very small to neglect, because we should make R1 R2 ايش؟ very large, because we need R1 and R2 to be large. We'll see why now. We'll see why later on. Now that is saying that the disadvantage of this design, that this VBE still a little bit temperature sensitive, but it's not as bad as VC. And even if VB is changed a little bit, it's not as big of a deal as VC, and the sensitivity is much less than VC. Another solution is to use different kinds of transistors. So for example, if you use a FET transistor, like JFET or MOSFET transistor, these kind of transistors are temperature independent. So they don't have this junction, BE junction, so they don't suffer from that temperature sensitivity. Then here what do you use? Use a FET transistor, which don't have this junction. Okay. One of the good features about shunt regulators is that they have internal or built-in short circuit protection. What do you mean by built-in short circuit protection? Assume that we have, so remember here I should have my load, right? My load is supposed to be here. But let's say by accident or so, due to any cause, a short circuit is induced here. So I have here a short circuit like that. So what is going to happen? The good thing is, because I have RS here, look, can I say that the whole circuit has been shorted out? يعني هل ال VN الحين, is the VN now going to be connected to a short circuit? No. This short circuit, what is it going to do? It's going to short out everything that's parallel with it. What do I have here parallel with this short circuit? I have this part. So all of this will be shorted out. See? All of it has been shorted out like that. This became like that. How about RS? RS is not parallel, so it's not going to be shorted out with it. So I still have I still have HRS. So in the case, worst case scenario, if you have a short circuit that happens here, this RS will protect you. And the current in the circuit is not going to be infinity. So usually, if you don't have this, يعني if I don't have RS, look in the case now, if I don't have RS here, صار عندي ايش؟ and I have the input connect to a short circuit. Right? Input connect to a short circuit. In this case, the current will be ايش? The current will be extremely high. But now since I have RS, what is going to be the current? IL. What is going to be the current? Is going to be equal to Vn divided by Rs, which is a limited value. Limited value. It is fine. So now my device, I have this built-in short circuit protection, which is extremely beneficial. Another important parameter when you talk about power regulators is efficiency. What do you mean by efficiency? Efficiency in engineering or in any engineering field, it means how much output power you are getting with respect to the input power how much output power I'm getting with respect to the input power that I'm giving. Because remember, this is the edge. Here I have my power or regulator right here. Here I'm giving it input voltage and I'm getting the output voltage like that. I'm getting input voltage here and I'm getting output voltage here. And this input voltage I'm giving, so this means that this power supply is absorbing this power. It's getting edge, it is absorbing or it is taking this input power, and my load is getting some output power. Now this input power actually is going to be divided between two things. This input power is going to be divided between two things. It's some part of it will go actually to the load, which I want, but you are going to see a large part of it actually will be absorbed inside here. We call it P regulation, or the power of the regulator. Why you have that? Because this regulator in order to work, it needs power. These are electronic components, right? So they need power to work. So they are going to absorb some power. The more power these things are going to absorb, the less efficiency I'm going to have. And this is very important, especially when I talk about power supplies, because power supplies, again, power. We're talking about power. Okay. So yes, I need to have good regulation. I need the voltage here to be constant, but at the same time, I don't want to pay a lot of power for that to happen. Okay. يعني if I pay here 6 watt, if I'm giving here 6 watt, and my device is only absorbing 1 watt, and the remaining 5 watt, where is it going to be? It will be here. So here I have 5 watt. So in that case, this is a very bad efficiency. I'm paying 6 watt, costly. Only 1 watt will be given to the load, and 5 will be lost inside the regulation. So this is a very bad efficiency. So what is the efficiency? How can I find it? It is equal to output power divided by the input power multiplied by 100%. I take it as a percentage. Now what is output power? Output power is actually very easy. The output power is equal to H. It's equal to I load. It's equal to this current and the I load multiplied by V out. So I load multiplied by V out. Or I can say it's equal to H I load square multiplied by RL. Or I can say it's equal to V out square divided by RL. Okay. So you can use any of the power equations that you are familiar with. So how about Pn? Pn is equal to H. Pn is equal to the input voltage multiplied by I source, Is. So Pn is equal to Vn multiplied by Is. Okay, so these are all these parameters we know how to find. So I can easily find what is the regulation of the efficiency of the regulator. How about this power regulation called the power wasted in the regulator components, P regulator or P regulation, the power I need that's consumed for the regulation action to happen. So P regulation is equal to, it's the difference, right? 6 minus 1, 5. So it's equal to Pn that you pay minus the power that will be delivered to the load. So in shunt regulators, the power dissipation of Rs, remember here I have Rs right here, right? or inside here. And the transistor accounts for most of the power wasted in the regulator. So RS with transistor are going to be where the majority of the power is going to be wasted. Actually يا شباب, actually another place that the power is going to be consumed is R1 and R2. Right? We're going to be in R1 R2. Remember, P, the efficiency is equal to H, or the power is equal to H, the dissipated power, or the absorbed power, اللي هنا, the absorbed power by these two resistors. تساوي ايش? It is equal to IR, I square R, right? So it's equal to I square R multiplied by R1 plus R2. هذه الباور dissipated here. The power dissipated here is equal to هذا واحد. So you can see that, yeah. So here these two things are going to absorb the power. But what we can do is what, if you look in this particular in this equation, what happens if I increase R1 and R2? If I increase in R1 and R2, yes, this part will go up. صح? Yes. If I increase R1 and R2, this will go up. But what will happen to I square? I square is actually going to go down, because the more you increase the power, the more the current will go down. But the idea is here, look here, I have square. فالتأثير حق النزول هذا, the effect of this going down, it's much bigger than this effect of this going up, because of this square. Okay, so how I can make this power small? How can I make this power absorbed inside the resistor here small? By increasing R1 R2. Okay, because they are connected in parallel. So according to KCL ما في current أصلا بينزل هنا بشكل كبير. If I increase R1 and R2 ما في current بينزل هنا. If you make them big enough, خلاص الكرنت هنا صار ايش؟ صار زيرو. Almost zero. Okay, so we get ايش؟ we get efficiency, we get high efficiency, because now I don't have a large power lost here. عشان كذا نقول ايش؟ نقول ان الباور ما بيكون is not going to be lost here, it's going to be lost here. And there's nothing I can do about this. لأن current, all the cases are going to move like that. Here I can make this current equal to zero. I can easily make it equal to zero by increasing R1 and R2. بس ما في شيء اقدر اسويه بالنسبه لايش لايس. It's constant. Okay? And RS will always be there. عشان كذا ايش هذا اكبر, this is the biggest source of power dissipation and the reduced efficiency. And in addition I have the transistor also, because the transistor needs to be biased. It needs to work in the it needs to be biased, so it needs to absorb some power as well. So what can we say here? I can increase R1 and R2. بدل ما اخلي مثلا R1 equal to 100, R2 equal to 200, what I can do is make it equal to ايش؟ 100k 200k. يعني ايش؟ increase R1 and R2 while keeping their ratio, يعني نسبتهم إلى بعض, their ratio the same. Okay, so by making the ratio the same. طيب, so now let's get to the requirements that we have here in this circuit, this example. So we have Vn equal to 15 volts, same as the previous example. Rs 10 ohm, Vz 6.2, Vb is 0.81, RL is 40, R2 is 250, R1 is 750. What are the approximate values of output voltage V out, input current Is, load current IL, and collector current IC? We need to get these parameters. Okay, so let's start by V out. What is V out? Remember, apply the reverse voltage by the rule equation. So we can say that V out, let me write it up here. V out is equal to R1. Here I have R1 down here. So R1 plus R2 divided by R1, not R2, multiplied by Vz plus Vb. So 250 plus 750 R1 is 750 multiplied by VZ is equal to how much? Question 6.2 plus 0.81 BE, and this gives me 9.35 volt. Sure, see, I can get 9.35 without needing to increase VZ to be in that same value. How about IS? IS is equal to VN minus VS minus V out, which we just found, divided by RS. Okay, so we use these values. 15 minus 9.35 divided by 40. No, 10. RS is equal to 10. So you get 565 milliampere. How about IL? IL is equal to V out over RL. This current. Same, it's the same expression, same ideas. So 9.35 divided by 40 equals to 234 milliampere. Now finally, IC, I will write it down here. IC, remember IC approximately equal to IS minus IL. So 565 minus 234 equal to 331. Yeah, sorry. Okay, so here, or you just find it here. Now this is ignoring IR, but if you want actually to see what is the exact value of IC, IC is exactly equal to H. This is approximately IS minus IR minus IL. So this is assuming in H, IR almost equal to 0. How much is IR? IR is equal to H. This is IR, right? Moving here. كم الفولتج هنا فوق هنا divided between them, across them, it is V out. So I can say R is equal to V out divided by R1 plus R2. So it is equal to H. How much is it's equal to 9.35 divided by 250 plus 750. So if you add these two together, this will be H 1000. So it's equal to 9.35 milliampere. So it's very small compared to H. This is 500, 200, 300, but this is just 9. Why is this small? Because R1 and R2 are large. You can even make this smaller by increasing this R1 and R2. لاحظ, what is the relationship between R1 and R2? In this case, R1 تساوي 3 times R2. 3 أضعاف R2. So by keeping this ratio the same, I can make this one, for example, 2K, make this one 6K. صح? Or make this one 10K, make this one 30K kilo ohms. So I'm keeping the ratio the same عشان الفولتج هنا يبقى زي ما هو. I don't change this voltage because here, look at the V out. V out تعتمد على النسبة هذه. So if I keep this ratio constant by using this, خلاص output voltage is not going to change. But what am I going to gain? I'm going to make this one small. What if this what happens if IR small? معناها PR, the power dissipated by the resistors, are also small. It means ايش? better efficiency. This symbol يا شباب is the symbol of efficiency, by the way. Efficiency. It's called eta. Eta usually in engineering and science is used for mostly to represent efficiency. Okay, so you can use this equation to see what is the exact value. And بيكون فرق, the difference is 9 milliampere, and it's going to be less than by 9 milliampere. So it's going to be 322 milliampere. Okay, in IR is absorbing 9 milliampere. So what is the approximate efficiency? How much is the regulation power, P regulator? So to get the efficiency, this is a symbol of the efficiency here. The efficiency is equal to P out over Pn divided by 100%. how much is Pn? Pn is equal to Vn multiplied by Is. صح؟ Pn is Vn multiplied by Is. هو كم؟ 15 multiplied by 65 milliampere. We get 8.48 watt. How about P out? P out I can find it as IL V out, or I can find it as IL square RL, or I can find it as V out square divided by RL. Use any of these equations. You get 2.19 watt. And you can already see how bad the efficiency is going to be, right? So the efficiency will be H this divided by this, multiplied by H, divided by 100, multiplied by 100. So you are getting H 25.8% only. What does it mean? It means that only 25% of the power, only 25% of the power that you are feeding to your, that you are giving here, this is Pn, only 25% of it will be H, will appear here. You pay here 8.5 watt, you're getting only 25% of it here. But where is the remaining 75%? The remaining 75%, where is it lost? It's lost inside here. So here you have 25%, here you are losing 75%. So P regulator is equal to H. P regulator is equal to Pn minus P out, right? So it's equal to 6.29 watt. Huge amount. H, huge amount. And actually this is a very big, this is the issue, a very big issue of H, shunt regulators. All shunt regulators suffer from H, low efficiencies because of RS, because of RS. It's always there. There's nothing you can do about it. You cannot decrease the current. And IS constant. So there is nothing you can do about it. Okay, that's why we suffer with these. We suffer with these shunt regulators, and that's why shunt regulators are not the best kind of regulators that are used, and series regulators are much more commonly used. So to conclude, the last thing here, we have a quick example to find the load regulation and line regulation. So very straightforward. When the shunt regulator, this shunt regulator we have here is built and tested, the following values are measured. V in L is equal to 9.91 volt, VFL is equal to 9.81 volt, VHL is equal to 9.94 volt, and VLL is equal to 9.79 volt. How much is the load regulation? So the load regulation is going to be this minus this divided by this, right? So we get ايش 1%, 1.02%. معناها ايش؟ معناها between the two extremes, when the load resistance is maximum, when the load resistance is minimum, الفولتج يتغير بمقدار only 1%. So if it's 10 volt, if you want it to be 10 volt, like that, almost 10 volt, شوف ان الاوتبوت voltage بس تغير بمقدار ايش؟ only 1%. How about the line regulation? Line regulation بيكون the voltage, the output voltage لما ال high line voltage becomes high 120 مثلا, and this is the output voltage when the line voltage is low, like 105. These are the fluctuations. So this minus this divided by this multiplied by 100%, you get 5.3%, which is also good. 1.53% is also good. So you can see that we are getting very good regulation, but at what cost? The cost of P regulator here. At the cost of P regulator. We are getting a very good regulation, but at the cost of low efficiency. We have a low efficiency right here, and this is the issue with shunt regulators. To calculate the maximum load currents in the previous examples, and you can see that as you have discussed with these shunt regulators, the maximum load current is approximately equal to the current through RS, right? So that this is going to be the worst case scenario, and IS in these examples that we solved throughout this lecture, 510, 565, and 593 milliampere. Okay, so you can see that shunt regulators are very good regulators in terms of regulation, but the issue is that this good regulation is at the cost of a very high power regulation power. So the efficiency becomes very, very small. And since we're talking about power supplies, from the name itself, power and efficiency are very, very important parameters. That's why shunt regulators are not always the most favorable choice, and series regulators are much more favorable, much more popular, and even integrated circuits regulator integrated circuits, they are based on series design. So inshallah next time we'll talk about series regulators. So thank you for listening, and see you next week inshallah.